Thanks, everyone. As Matthew mentioned, I am Mahmoud Hashemi, and without doubt, my slides will show up any moment. There we go. Okay, so yeah, my name is Mahmoud Hashemi, and I'm here to talk to you today about production-grade packaging with Anaconda. So without any further ado, let's get this party started. Packaging. It's presumably why you walked into the room, and it's also in the name of the title. What is it, though? So in the biggest font I could, I defined it as turning code into a deployable archive. But I think the real question that we're all trying to answer here today is how? How do we do this, especially in sort of an industrial, service-based kind of setting? So they always say, like, start a presentation with a quote. Here's a real-world quote from my very first project at PayPal. I was very busy with the architecture of the application. I wanted to use all the best libraries, all the best practices in Python. But the packaging section, I left TBD, And I feel like this is a very common mistake among naive, young, pure developers straight out of school. So here are some examples of these rookie mistakes, this developer naivete. Let me know if you recognize any of these. Packaging is just the last step in software development. That's what the mistake I was making earlier. And then, you figure we'll just fudge something at the end, and we'll take the B, right? It's like a test. You fill it out, and if you miss the last question, who cares? You get an 85%. That's pretty good. You can graduate with that. But let me tell you, with packaging, there is no B. You either ship it or you take the L. You can't take a B. All right. So, and finally, one thinks that, like, if I can build it, surely someone will ship it. I'm working in an enterprise. It's a 10,000-person organization. I'm not going to build something and just be left there listing. But unfortunately, this actually does happen. I've myself witnessed a project. Thankfully, I was more experienced at the time and dodged that bullet. But I've witnessed projects with 3 developers working for months. When they actually get to time to ship it, they talk about their requirements with the operations group. And operations is like, yeah, actually, we can ship that. Give us 3 to 4 months and, authorization to spend about $1 million, and we'll get that shipped for you. I've never seen a project die faster. So these are some of the naive mistakes that developers can make. Let's look at a quote from a much smarter, more experienced person. The first 90% of the code accounts for the first 90% of development time. The last 10% of the code accounts for the other 90% of development time. And this is from Tom Cargill of Bell Labs. So this is a long-standing, well-known quote. I'm pretty sure he was talking about packaging. I'm pretty sure he was talking about getting that last 10%, right? You thought you could take the B, but you couldn't. And this is actually known as the 90-90 rule. So anytime this comes up around you, feel free to cite this from Tom Cargill. So with that bit of wisdom, let's look at how to avoid that kind of scenario. And for that sort of, to avoid that kind of scenario, I recommend a technique known as production-first development. What am I talking about here? It just means you have to ask the question, where is the code going? Before you even write the very first line, think about how far away it's going to go and what the accommodations are when it gets there. Here we are at a conference, right? And I'm sure a lot of you packed something that looks like this, right? And this was because you were packing knowing that you were going to be staying in a hotel room, right? But if your deployment target was a parking lot, because this is America and this is a Python conference, I'm pretty sure someone in here brought one of these, right? And you packed quite differently, I'm sure. If you've got a Winnebago and your production target is a parking lot, you're going to pack differently than if you have a hotel room. So with that in mind, let's take a look at what Python has to offer for packaging, right? They're the best practices. I Googled them for you, right? You can put those laptops away. So at the very smallest level, you have standalone modules. This is the smallest unit of Python. It's a PY file, right? And if you write it correctly, you can basically redistribute a PY file, a script, if you would. And it's standalone. It only imports from the standard library. That means that your production target is some version of Python. And you can make some very useful applications like this. Some examples would be the schema library, Ash's templating library, Boltons, which is another one that I maintain that's rather popular, and bottle.py, there are a lot of web services launched with bottle.py. You target Python, makes it easy to distribute, easy to integrate. You have one file, you can hash it, you can move it around, it'll work. And this leads to also using those projects inside of other projects before packaging got fixed, as it were. You would just vendor that dependency in, so you wouldn't have to worry about setup.py and other sorts of dependencies. That leads us to the molecule to the module's atom, right? The pure Python package. This is just a directory full of those py files, right? And I put package here in quotes for a reason we'll get to in a moment. It generally includes dunder init, and there are lots of examples of these, more than I could possibly name, 80,000 or so on PyPI. Django, requests, hyperlink, face. And these are very easy to install with pip, because pip installs packages, right? Everyone here used pip? Maybe the wrong conference to ask at? All right. But no, we've all used pip, and it installs packages, right? Actually, right? Sorry to get technical at a technical conference, but pip doesn't install packages. It actually installs distributions, right? The things that live on PyPI, the Python package index, are distributions. Sort of fuzzy naming here. The packages in Python are not proper packages. On the very first slide, what do we talk about? Redistributable archives, right? We want single files that are hashable, that you can name with metadata inside of them. You don't want messy directories full of possibly PYCs and other messy bits. Proper packages got to be distributable. A distribution is an archive of 0 or more packages. They can include packages and modules, kind of a small distinction. And I'm sure some of you have used other languages by now, Go, JavaScript, and so forth, and you might be wondering, why did Python take these pains to create this extra layer that has to be explained every time someone learns packaging in Python? There are a couple of motivational case studies that I want to point out that make distributions kind of great. So has anyone here used the Python imaging library, PIL? Oh yeah, I see hands. Okay. So PIL, as you may know, the maintenance kind of fell off after a while. But because it's open source and it's free software, wonderfully people came along and picked up the torch and created a new library called Pillow. And interestingly, it is basically a drop-in replacement for PIL. You can simply pip install Pillow instead of PIL, and you don't even need to change your imports. It provides the same package in a different distribution, which allows you to sort of like keep your projects rolling. It's not that way when you depend directly on a GitHub repo. You know who I'm talking about. Let's go. All right, so PyCrypto is another example of this. Similarly, fell to become somewhat unmaintained. You probably shouldn't be using it anyways, but if you have a legacy piece of software, there's PyCrypto Dome, which is at least better than PyCrypto. Cryptography is a better library overall for most cases. But yes, distributions are built by setup tools through setup.py. And the simplest version of this is the sdist, S standing for source, and dist standing for distribution. So it's a simple source-only tar-gz. Nice and mature, simple. But that's not the whole enchilada. The big one that we need to talk about here is the full package. If you Google Python packaging, you're going to hear a lot about this one. Python's more than py files. We have to interoperate with Python, C, Fortran, all sorts of stuff, assembly. There's a wide world of software out there that isn't written in Python quite yet. And Python loves that sort of interoperability and performance. I think everyone here benefits from libraries like Pillow, gevent, LXML, so forth. And so for this, the Python packaging authority has sort of pushed for the wheel. Right? And you'll see there's a wheel of cheese because PyPI is known as the cheese shop because that's a Monty Python joke. We all use a language named after kind of a joke. So it goes along with that. Big wheel of cheese. All right. The shiny new binary distribution, or bdist. Binary distribution, bdist. sdist, source distribution. Binary distribution, bdist. This allows us to support most Windows, Mac, and Linux machines with no compiler necessary. Stuff installs very quickly, and it just works, apparently, most of the time, right? So, Python setup.py, sdist, bdist_wheel, upload. If you Google Python packaging, you'll see that this is the modern way to build and upload a Python package. This is how you package it, and this is how you distribute it. So that's what I have for you today. Questions? Any questions? Yes. Thank you. Show's over. Check out my projects, github.com/Mahmoud. Nailed it. All right. No, of course, big questions. Lots of big questions. I got 39 minutes of questions. Okay. Yeah, so packaging is never as easy as the docs make it out to be, right? And specifically, Python's docs talk a lot about these options and leave the rest of it very hazy. So one of the biggest questions is, what about system libraries? I just finished saying the world is not written in Python yet, right? We have wonderful software written in C, C++, and Fortran, and so forth. I say it's wonderful because it's pre-built, and I don't have to build it. So there are these pre-built standard libraries that are managed through the operating system in many cases. If you've ever seen an error talking about a DLL or an SO, this is what that is. libcrypto from OpenSSL, great example. libxml2, libpng. These are all examples of things not written in Python, but Python libraries depend on to use. And so this is where we get into static versus dynamic linking. How many people have spent, say, a few hours trying to figure this out in the past? Oh boy, a lot of hands. Right conference asked that question. Okay, so I'm not going to completely explain this to you, right? But basically with wheels, the idea is that you can make big wheels that have these libraries compiled into them. But especially with security stuff, this has a problem, right? So basically your Python library can go out of date as soon as a CVE gets filed on OpenSSL. Right? And your admins, your IT people, whomever, cannot just basically go update that OpenSSL without also updating your Python software. This is mixing layers, and it can be a big management headache. So these big wheels still have their use, absolutely, but they're not really a complete solution. And really, that's where conda comes in. Right? You can use conda to have Python libraries and applications depend on system libraries and things not written in Python. That's really the beauty of the whole system. It's very simple and hopefully easy to explain once you've gone through a bit of this packaging headache. So it actually took me a surprisingly long time to see through the veil of Python's best practices for packaging and realize why conda exists. But after this, hopefully you agree with me. It seems like Python's provided packaging from the PyPI and so forth solves a much smaller problem than packaging Python. You can write all sorts of things in Python, and not all of them can be packaged using the PSF's recommendations. So how do we actually do that? Well, first let's review what we've covered so far. And I need to prep you for a slide that's coming up. Okay. So just to talk about what we've talked about so far, PY files are independently redistributable as standalone modules. You can also put PY files inside of an sdist or pure Python package. And you can put pure Python packages and much more, including some statically compiled in system libraries, inside of a wheel. And even bigger than that, you can use conda to get Python and system libraries. And so I've sort of structured this as kind of a gradient with, I think you guys get the thing. Hopefully you get it. I spent hours creating these circles. Okay. All right. But wait, right? That's not the whole story. The other term in the title, production, right? What is the first thing in this word? It's product. You can't ship to production without a product. And I think this was the thing as a junior engineer that I started to realize is that these best practices for shipping libraries don't necessarily compose into something that works for me with my need to ship an application to production. So really there are two kinds of packages. You have libraries. These are the things that we work with every single day in, day out. We're creating these things, installing these things, reading their docs. We're composing libraries. But libraries are rarely a product. Maybe an SDK, arguably, like in video game industry, they do this sort of thing. But generally, they're not a product. Applications, on the other hand, these are services and other products with high-level non-code interfaces for maybe a less technical audience. And this is where most of the products live. These are the money makers. So that brings me to my next point that I always have to drill home to people, junior engineers especially, who have done the right thing and read the docs. PyPI is not an app store. You can't just put your code up there and use it like an application. Maybe you can if you have a developer audience, but realistically, pip and PyPI are not general purpose, but Python is. So there's this whole space of packaging that we have to talk about. We got some time to talk about it too. But yeah, let me drive home. Don't pip install production, especially not from PyPI. Right? Pip requires a developer to be present to debug and resolve all sorts of issues, everything from network connectivity issues to, literally installing the wrong requirements if there are conflicts. Because there's no dependency resolution or transactional installs. Conda has both of these things, I should say. But even dev tools, like I said, you can ship code to developers. Even dev tools work better with something like pipsy. Has anyone here heard of pipsy? Okay, so basically what pipsy does is it makes a virtual env for a given dev tool. So you want to install Pelican or some other thing that you can install from pip and it works as a command line application. Pipsy makes a virtual env for that so that any other installs don't break that particular tool. It's pretty nice. And it follows the convention that every application deserves its own environment. Now we can finally talk about the right ways to ship product. And I'm going to provide a summary. Hopefully that you saw that last slide and you're prepared for this pattern because there was no way to make these transitions work. Here is a summary of shipping product in Python in 2018. Okay? And it's going to follow a very similar pattern to what we talked about with libraries. So at the center here, at the most basic, if you're targeting a working Python install, you can turn your application into what's called a PEX, a Python executable. It's part of the Pants suite from Twitter and so forth. I've shipped applications like this. A PEX can be a fantastic way to ship around a simple command line tool. The second one here, Anaconda, everyone is hopefully pretty familiar. We're going to be talking a lot about that. But if your customers all have Anaconda installed, you can target Anaconda, and you can make that into your packaging system. The third one is very interesting, freezers. Anyone here ever used a freezer? Like shipping an actual consumer application? I see one hand. Okay. The lights are bright, though. He's tested the freezers. Ilan has tested the freezers. Okay. So freezers are the way that you basically include not just the libraries and your business logic, but also Python itself, all frozen together into something like a native app. And there are many examples of this. I'm pretty sure a bunch of game engines use Python for scripting internally, and they have to freeze the actual Python runtime into their executable. But there's also, I think Deluge is a Python application that is written with Qt, and so it's a native application on a bunch of different platforms that it supports, all frozen together. Don't quote me on it, though. There are plenty of examples of freezers. Okay, images, or user space images, is something that we'll come to, but this allows us to include not just Python, but also system libraries. Oh, and then we also have containers. Containers we'll be talking quite a bit more about soon. But these are effectively user space images that get a sandbox. Number 6 and 7 are very interesting, though. They're often elided in a packaging discussion, but we have to touch on them. Virtual machines allow us to not only include system libraries, Python, your business logic, everything, but also a kernel. So you're really targeting a user's hypervisor. And it's a genuine way that you can ship around a product. And number 7 is maybe the most interesting packaging solution of all. It's to create a literal physical package with your code living on it and selling it that way. This appliance-driven packaging thing is the driver for a huge industry out there. And you can find routers out there that include little operating system things on them that are written in Python that are pluggable and so forth. So like I said, we're going to mostly be focusing on Anaconda and containers today. But if you want to go through all those things in more detail, I have given another talk where I managed to use my circle thing. And you can see the rest of it at this URL. So yeah, without any further ado, let's start talking about putting Anaconda into production. Bigger stakes, bigger snakes. All right. So many years ago, I worked at a little company called PayPal, right? And I was straight out of school, tasked with shipping an application to production, and my options were to write it in C++ or Bash or something. I opted for Python for reasons I think we can all identify with. That was in 2009. And we got the code done really quick. And then actually shipping it to production took 10 months. So things were in pretty bad states. But we managed to still be faster than the other guys. And so that meant, like, modicum of success led to us creating a team in 2011. And eventually, we had 30-plus mid-tier applications, services, and batch jobs. And the batch jobs is an interesting one because people often think that apps and services, wow, you got to have really high SLAs. Batch jobs have exactly one chance to run nightly, right? And if you mess up a batch job that is going to resolve $1 million in transactions, right, then, you know, that's it, right? If you mess up that batch job, you have 24 hours to fix the problem that you created, or the government will fine you. So we were very honored when people started using Python for batch jobs at PayPal. But in terms of our services, we had, in terms of max single service volume, we had 1.2 billion requests per day running on Python, with very low latency, I should add, thanks to Python. And within a single service, we were doing 10,000 requests per second per worker, basically per CPU, which is something we were very proud of because we were the only stack that could hit that sort of throughput. Okay. So yeah, all of this was sort of structured around the multi-protocol service-focused G-event-based framework, and it was pretty successful. We had hundreds of users, almost all of them were grassroots, and we even managed to open source it just sort of as a reference implementation. It's not kept in track with the internal one. That takes a lot of work, as the Anaconda people know. You either have to go fully open source or just throw one over the wall as a reference, maybe. But yeah, so back to our users. Here's our team, by the way. 5 of us, me, Kurt, Chris, Mark, Guido. Yeah, so we had hundreds of users, almost all of them grassroots. You don't grow to that size without saying yes a lot, right? And so before we knew it, by 2014, skipping to the middle here, we were supporting more platforms than any other stack, right? We had Linux, 32-bit and 64-bit, 2.6 and 2.7. We had Mac, 64-bit 2.7, Solaris, 32-bit 2.7, Windows, 32-bit 2.7. And there were 5 of us, right? So I'm going to do some quick math for you, right? We had 8 of these environments. We only supported a core of 10 libraries that were guaranteed to work that had binary dependencies. And that's 5 team members. So quick math here, carry the 1. That's like infinity constant static builds all the time, right? And it was great because it just worked for our users. They loved having these static builds that just worked. But it definitely put a strain on us. And you know, we were trying to grow the team, and we were getting stressed out. And I was saying, like, if only there were some sort of cross-platform package manager, right? And I'm asking myself, I'm like, what's an example of a cross-platform package manager that can help us in this regard, right? Is it package source? It's like, no, man, I don't want something from the BSD world. That's not going to help me. We use Linux. Nix, is that what I'm looking for? Is that a cross-platform package manager that's going to help me? It's like, well, yes, but it's not going to help me at work. And Steam, no, you're just pulling my leg, right? Right? But interestingly, this is the full list of cross-platform package managers, right? Supporting more than one operating system. It's a surprisingly rare breed. And we're very lucky to have one. It's like, oh, Anaconda. Here's one right here that basically supports Python first, right? It's not just that it's cross-platform package management that I can basically conda install Emacs with, right? It's also Python first. So we're very hashtag blessed. All right. Because I look at this Anaconda environment support matrix, and I'm like, oh wow, they got Linux, 32-bit, 64-bit, 2.7, Mac, 64-bit 2.7, Windows, 32-bit 2.7. You know, that's 80% environment coverage, right? The Solaris guys, you know, they can take care of themselves, and they've got 500 plus packages, right? We can really expand our reach because people that are wanting to use NumPy and Pandas and some of these libraries were not easy to get statically compiled. So that's infinity percent better. That's way, way better. And that's basically what we aim to do. So Anaconda in PayPal Live, production first, development in practice. I'm not going to make the same mistakes I made in my youth. I looked very closely. I knew PayPal was on RHEL 5. Before that, they were on Red Hat 6.2. Like RHEL 5 was a big step up. That has Python 2.4 on it, right? This is, I just said, like 2015. And we sort of tried to work through like the enterprise governance and architecture council and so forth, and we got this mix of 2.6 and 2.7 added on all the like Linux boxes. It was not really a very sound foundation. And there was no Anaconda. We couldn't convince them to just put Anaconda on every machine and keep it up to date. So we couldn't just target a conda install. We had to go to production, right? Which meant that we had to find a way to make an RPM. And the way we did that was we decided to put miniconda in an RPM. And I'm a fan of keeping it simple. So here's 3 steps to a conda RPM, how it actually happened, right? There's one way to box a snake. Once you have your application and it's working, right, you have your requirements in hand. You go onto a stage machine or something that resembles live. That, thankfully, we did have at PayPal. So we went into the stage machines, and we would do a conda install with a -- download only. New option didn't exist at the time, but this is exactly what we wanted. We would take all of the tar BZ2s that got put into the packages directory, as well as a miniconda, and shove it into an RPM. Very small builder script for that RPM. And in that RPM's post-install section, right, then you just put a tiny little installer script that runs conda install. So it's not really making a relocatable conda environment. This is really dead simple, but it runs the installer at RPM install time. It's not really taking advantage of every single RPM feature out there, but it did work. Operations was okay with us going to live with this, and it worked for quite a while, for some advanced use cases using NumPy and so forth. So we were ready to test and deploy, and them being satisfied, this worked. We wrote it up on the PayPal engineering blog, Python packaging at PayPal. Sometimes you just got to say, hey, life can be easy. And that's what that blog post says. And most importantly, we put that little tiny installer script up in our open source repo. But people who are much smarter than me actually have found other ways to do it correctly. Thankfully, that's the beauty of working in open source. Since then, I've found repos like SnakePit, conda RPMs, and this new one that is maybe not ready to go, but conda pack. And all of these apparently make sort of relocatable conda envs, which basically are much more native than what we did. Maybe we would have used those at the time. So try them out. If you have RPM as an installation target, RPM yourself a conda today. But that was then, and this is now, right? RPMs and Debians it's just so 90s, We got to do something cool. Maturity, that's not cool. All right, so putting Anaconda into a containerized environment. We did it. I'm going to tell you how. So in order for this to make sense, we need to backtrack a bit and talk about how Anaconda works, right? Has anyone here actually gone into that Anaconda 2 or Anaconda 3 directory that gets created in your home directory to see what lies under the hood? Okay, so many of you. If you haven't, I really recommend it. It's sitting right there, and it's totally legal. You can go take a look. It's really a whole new ecosystem. And by ecosystem here, I mean a user space. So I don't know if you guys can all see this, but if you look in that directory, either up here or on your laptops, you'll see that there is a lib, a bin, an include, an etc, all these different directories that look a heck of a lot like the root Unix file system. And wouldn't you believe it, that's basically the beauty of Conda's implementation. It relies on OS and Python features, such as that user space file system layout. So Python, the way that it runs, I don't know if there's a term for this, but we called it in our team Python landmarking. This is sort of the way virtual envs work too. When you go bin Python, Python knows to look up a directory, and then for a lib directory there, and look for a Python 2.7 or 3 whatever, and then site packages, right? This is sort of how Python got around your file system, and it was just all relative imports in a way. And so a lot of other applications work that way. The paths and the linking are all going to work that way. And so what you have is sort of like this mini user space underneath the hood of Anaconda. And when that doesn't work, you always have patch elf. So Okay. So with that understood, now I think you're ready to sort of see where these newfangled technologies are coming from. User space images, kind of like Docker images, but user space images are like Anaconda meets your old auto-run CD. Anyone else have nostalgic memories of like popping in a SimCity CD and then like it would go in and then something would come up and it'd say, do you want to play SimCity 2000? I'm like, yeah. Anyways, and if you ever saw inside of one of those CDs, you'd see what was making it happen. There was an autorun.inf, not an INI, an inf. So basically, this is that same thing. It's your user space getting its own partition. In fact, the first version of this sort of thing that I saw was literally an ISO 9660, CD formatted image that basically, when you would click on it, would mount itself. And the implementation of that is called app image. And this, I think, predates Docker. So app image is a way to have a self-contained single executable archive, just chmod plus X on it, and you can double-click it, and it'll run. For an example of this, you can check out KDNLive. It's a video editing application. There are a lot of them that use app image, but for our example, I basically took another screenshot to see what's inside that mounted partition. Inside of here, you'll see that there's a lib, an etc, a user with a bin inside, and there's also like this app run, which is sort of like that autorun.inf of the autorun CDs of old. And you also have dir icon, which is the picture that it'll have on your desktop. So if you want to learn more about how user space images work, you can go to app image. It doesn't have a big marketing group. It doesn't have VC behind it, but it's very sort of viable technology. I'm curious to see more people use it in the server environment. Wink, wink. And you can also see the KDNLive sort of build recipe for their app image, which is available online there too. Now we're finally ready to talk about containers. And containers is, of course, in quotes because, as some people are fond of saying, containers aren't a real thing. In fact, they are simply user space images with added sandboxing and distribution. So sandboxing here is basically about creating a security model around it where you grant it specific privileges instead of sort of blacklisting all the others resources on the system. You don't have to worry about your permissions being wrong elsewhere on the file system because this thing is sealed tightly. That's the idea anyways. Kind of like Tupperware, it's reusable and disposable, but you got to check that seal. Okay. I think what's much more important about containers as we know them is that they have distribution figured out to a certain degree, right? So an example of this is Flatpak and Snappy. These are the debs and RPMs of our millennium. Basically, Red Hat has found a way to fight with Canonical over how to ship Linux desktop applications. 2018 is definitely the year of the Linux desktop. And so we have Flatpak and Snappy, which are containers, basically with user space images distributed by your operating system in sort of an app store type setting. And that, of course, brings us to the server equivalent of these technologies, which is basically the big one, the big whale in the room, Docker, sometimes called Moby. So basically, after PayPal, we were looking for even steeper hills to climb to challenge our Python infrastructure skills. So we found a startup that not only had a legacy environment like PayPal's, but they also had a legacy code base. How legacy, you say? It's about 150,000 commits and 12 plus services, all living in a monolith. It had been around for a while and, posed quite the sort of engineering excitement challenge. And for their environment, they had CentOS 6 with Python 2.6 and LXC. They were early adopters of the container scheme. But because they had a local development environment of a Mac, because they run as an app, and everyone has to be able to build an iOS app, and if you want to build an iOS app, you have to have a Mac. So because of the 100% Mac local dev, that was a very exciting sort of challenge to look forward to, too. So yeah, we were given one mission. That's upgrade the stack from 2009 to 2017 in one fell swoop. And of course, we needed every trick and card up our sleeve. So that definitely meant that Conda is going to make an appearance. Here's our team, by the way, the A team. All right. So yeah, our approach to this was, again, production-first development. We want to close the rift between that local and production. We figured it's better to target Linux than Mac OS. As many of you have known, if you do development on Mac, right, homebrew is becoming increasingly untenable in some ways, and Mac is very intent on disrupting the developer, removing OpenSSL, shifting libraries here and there, et cetera, et cetera. So we figured it's probably a safer bet to develop straight on the production environment as much as possible. So we figured what we need is virtualization, and ironically enough, Docker had this native macOS virtualization that was much lighter weight than some of the other options, such as Docker Machine, which was built on VirtualBox, and Minikube. Later we shifted to Docker Machine and then Minikube, but that's how we started out. Our main intent was to avoid lethal exposure of Docker to the standard day-to-day application developer. Right? We don't want people outside of our team spending multiple hours a day in GitHub issues from 2014 that are still somehow open, right? That was what we didn't want for our application development group. And we also wanted to account for new tools. So we also upgraded the Git to use GitLab, and we had Kubernetes later on. And so what we came up for this is basically a dev tool to unite them all called OpenSky. It was big, blue, and cloud-ready. So the goal of Sky was to make it so that you could split out a service from the monolith and have a single configuration file in there that would be able to specify how to build images for local, stage, and production. And we wanted to be able to make it have actual library dependencies instead of all the source being checked into a single Git repo. So we gave it binary dependencies from yum, conda, pip, and Sky because there was that giant monolith. So how do we mix all these together? Basically, a couple of details first. The service dependencies, since we basically want to run a local version of production, like a local swarm, those would be specified in terms of Docker images. And the tool itself was distributed as PEX, our old friend PEX from the middle of the shipping product slide. We had plugins and core sort of built and bundled together, and we could just IM it to each other or a link to a release repo, that sort of thing. And I'm very pleased to say that I actually got my old boss to open source this. So the core of this is actually open sourced. Again, not kept in sync with the internal version, but as a reference, if you're curious about any of these sorts of details, how we did configuration and plugins and so forth, it is online now. And how it's implemented, right, is on top of Conda, like I said. So Conda is a core part of how it worked. And the good news is that Conda in containers just kind of works, despite the curveballs Docker wants to throw your way. So again, we had the bring your own mini Conda approach. We still want to stay on top of CentOS, so we were on CentOS 7s, as a base image, and we put mini Conda on there as soon as we could. Again, we had a custom installer script. I do not recommend building with Docker build. It's anemic. Docker build is maybe the most anemic part of Docker, short of the registry. So basically, because that instrumentation was severely lacking, didn't give you timings, and it is sort of prone to layer proliferation, we had our own installer script, part of the open source repo. And I'll highlight a few implementation details if for some reason you want to embark on this too. Basically, we would run Conda stuff after yum and before pip. This actually seemed to work more or less fine for mixing these different dependencies. When dealing with images, size is always an issue. So I don't know if this is a very unpopular thing, but it worked for us. We put no MKL into the build commands or the dependencies for Conda by default because it saves us 600 megs, right? And as soon as you can make images very quickly, people are going to start making images very quickly, and your Docker registry is going to be very sad as that 600 megs just multiplies. So unless you really need the speed, just use no MKL. And also check out conda clean. It's a good subcommand. It might save you a few of those megs too. Nothing like no MKL, but still handy. Another thing that I tossed in there, can't remember exactly why, but I think it was important. No channel priority. We were pulling from many different channels. We wanted the developer to be able to just throw conda dependencies into their YAML file, and some people got things twisted up, and no channel priority simply fixed it. That's a really nice conda option just for that. So to wrap things up into a nice, neat package, right? To reiterate, production first development, always think about what your target is and choose the packaging solution best for that, right? Are you targeting Python itself? Maybe you want to have a PEX, right? Are you targeting conda? You can do a conda package. Are you targeting an operating system? You should have a native package like an RPM or a deb. Maybe you need to do a freeze so it runs like an application on the consumer laptop, et cetera, et cetera. I have a whole nother talk called the packaging gradient that goes through all of that decision tree. With Anaconda, in case it wasn't clear, the main reason we went with it wasn't just the static builds, but also because so many people wanted to use all those Python packages, and it was just sitting there waiting for us, like an oasis of pre-builts on anaconda.org. So leverage that ecosystem. And yeah, I'm also here to sort of iterate that conda inside OS packages works and is very viable for shipping services to a production environment. And it also works inside of containers. Conda is definitely not the trickiest part of having a containerized ecosystem. So yeah, as one final note, simple is better than complex. Do what works for you, and hopefully you'll share it with the rest of us when it works. Thank you.